this is our piece of hardware that we have. We mentioned about the OBD2 and so on, and these are the several sensors which are available as part of the engine ECU. Now where does IoT come in here? Correct, that is your immediate question after listening so much. Where do we fit in our IoT related part into this course? To explain that, it is useful to know that these 5 sensors give you 5 different outputs, correct. You should make some sense out of those outputs which are given, and you should be able to say something is malfunctioning, something is incorrect, or everything is okay. Even it can also be that, right, things when everything is fine you do not have to do anything. So even to get to a point where everything is normal or something is anomalous, you must be able to process all these signals, combine them in some way, interpret them in some way, and then arrive at something useful. All of that essentially means that you need a framework under which such anomaly detections or event processing actually happens. For that, what they normally do is they use what is known as a complex event processor. It is called CEP. Complex event processing is nothing but it is a method of tracking and analyzing, okay, this is very important, streams of data or streams of now what I would call information, okay. In other words, it is mostly data which is coming from the sensors about things that happen and deriving a conclusion from them, okay. This is the most important thing. So you need a CEP system, a framework under which CEP is possible. I will go through this paper for you, and this is a nice paper which sort of summarizes where IoT can be a big driver. So this is a paper on cloud based driver monitoring and vehicle diagnostic with OBD2 telematics. As you know, the title is quite obvious, you know everything about OBD2 now. So let us look up this paper. They present a cloud based vehicular data acquisition and analytics for real time driver behavior monitoring, trip analysis and all of that, and I will skip all the remaining parts because they are not important. What is important here is the following, and this is a very critical thing which you must note. You have a vehicle, quickly this is the vehicle, there is perhaps 4G, 5G, call it whatever, which is connecting to the cloud, and there is a server which is in the back end. Alright, whatever decisions that have to be taken quickly are taken in what is known as fast loop. For example, the fact that you want to check an anomaly of a sensor which can be done over a longer time period, that you can push it to the back end if you want to do something there. But if you have to take a decision with respect to some, let us say, driver behavior which can be disastrous to the vehicle and occupants who are sitting in the vehicle at that point in time, that can't happen over a back end system, that would not work, okay. So what should be taken into fast loop and what should be taken into slow loop is the question. Data is being generated inside this vehicle, and what should be processed right there, right then and there, and what can be pushed to the cloud for processing at the back end is really a question. And this partitioning, slow loop, fast loop partitioning is very critical, okay. and you must learn the trick of thinking this should be done here, that should be done there, and so on and so forth. This will keep coming back to you as a recurring theme, fast loop and slow loop. So please note, algorithms that you design, the systems that you put in place will all be with respect to the fast loop and the slow loop algorithms which will have to be done. Fast loop means indeed real time, and if you say a slow loop, it can be offline, so it need not be real time. So you can say real time and near real time. Near real time, it is something that you can take an action when the bus or the vehicle reaches the nearest service station, you may have to show it up. It is not urgent at the moment, but it is required to be done immediately on arriving at a particular spot. Think of what a pilot and the first officer would have to do when there is smoke inside a plane. Okay, that data that is gathered by the set of sensors inside a plane, they can't be waiting for a command from the back end. What should be done after analyzing the data from the sensors? The pilots have to take an action. They have to either land somewhere in the nearest airport, get the passengers out from the plane, right. So that is a fast action and a fast loop action which humans have to themselves have to perform. But if you look at autonomous vehicles and so on, there are not going to be any more humans in the loop, which means data and sensors and the processors and the intelligence and the CPUs have to take this decision as though they were like humans taking that decision at real high speed and in real time. So therefore real timeness is an important thing. So this paper is actually focusing on that aspect of doing something in real time and putting something back in slow loop. So CEP is split into two parts. There is a CEP running on the vehicle, like for instance you see CEP engine at the smartphone, like it is like that something that is inside the vehicle, and then there is a CEP on the cloud as well. CEP on the cloud detects reckless driving in real time based on sensor data provided through OBD, okay, and CEP engine at the smartphone can alert the driver about rising coolant temperature and rapid fuel drops. This is something that has to be done right then and there. If a driver is reckless and accelerating, decelerating and all that, it is still okay. You can report about a driver's bad behavior to the owner of your taxi after you get off, but this is something that you cannot afford, right, rising coolant temperature and rapid fuel drop. So you can see it is all about fast loops and slow loops. Also the fact that sensors failure prediction is an important aspect of this whole paper, and they talk about IoT sensors failing, and therefore predicting that there is a failure is also an important thing. But you know, failure prediction is typically done through take data and do some form of regression analysis, and that is what this paper is also talking about. And interestingly there is an app which you can download from Google Play, and I did play with it. So now let us look at what this paper is saying in detail. OBD2, we know what OBD2 is, and it is giving you ECU related parameters. This whole paper is about ECU related, so it is all about speed, engine RPM, coolant temperature, fuel rate and oxygen sensor, almost the same set of sensors that we have with us in our lab here, the ECU SIM hardware that we have. And we can skip this part because this is talking about OBD2 protocol and all that, so we can leave that. So now let us go down to the actual part. This paper is actually trying to say that there is a gap in existing literature, and this is the gap that they are actually trying to fill, where there is information about vehicle, there is some scattered information about several aspects. Research is being carried out in the area of vehicle monitoring, but fault detection is something that people have not really looked at. So this is a single system which not only does vehicle monitoring but also can do fault detection. So apart from that, this is also talking about reckless driving, driving anomaly, vehicle sensor failure prediction, high fuel consumption, high coolant temperature, alert generation and trip detail and so on. Okay, so if you read this paper, you will see that these are handled separately, each one has a section by itself, and alerts are generated both in the back end as well as in the app, which is held by the driver or some occupant inside the vehicle. So that is the key thing, and they have an architecture here. This is nice, simple to understand. You have data coming in from OBD2 and then you upload it to use this as a sort of a gateway system where also the CEP algorithms are running. CEP can run here on this phone, right, and or whatever you have partitioned as something that should go to the back end, use a 3G link from the phone and then put it to the CEP BAM servers, business activity monitor as it is called. So this is a nice framework under which the authors have put this framework in place. Alright, so before we go on to that, so how do you receive data from the OBD2? This is mentioned here. Parameter IDs we already know. You want to monitor the vehicle now, right. So what you do is, the app consists of a real time data processor which is based on some framework called SIDI, WSO2 SIDI, which has the capability to act according to predefined set of queries and has been ultimately used to monitor the vehicle using OBD2. You can give queries are added as alert to the driver if the vehicle is running with high fuel consumption or high coolant temperature for a considerably long period of time. I mentioned to you many times that getting this information in isolation is not going to help, but if you really feed this information to the cloud along with the location information of the vehicle, then it is a lot more valuable. Time, date and location information along with this high fuel consumption and high coolant temperature adds a lot more value. You actually know where the vehicle is, what is the terrain and what is the condition under which the system actually has this problem. In airplanes also it is the same. A bunch of sensors which are connected inside the plane are all recorded in a flight data recorder, okay, this is called the FDR system. Then you have another system which is called the cockpit voice recorder. This is just capturing the conversations between the captain and the first officer, right, or any announcements and so on are all captured there. I mean whatever is happening in the cockpit, if the pilot is making an announcement to the cabin side, that part is also captured. So there is conversations part and then there is the actual sensor data part. Both are separately recorded on separate systems, and you can have redundant boxes so that even if you know for some reason some part of the plane you cannot get it from the wreckage, you are not able to locate the wreckage, at least from the other part of the plane maybe somewhere it is kept and then you can pull it out. So it is simultaneously recorded on more than one system so that it is easy for recovery and for diagnosis and so on. Same with thing here, you will have to add that part of the system of location information so that it adds value to whatever is being said. So complex event processing can be regarded as a service, and you can see that the portion of processing is handled by the Android app, and before transmitting data, that means fast looping is done first and then the backend server allowing less consumption of bandwidth. There is the library WSO2 SIDI which is the core processing engine and used for processing this. So this is also mentioned here. Okay, the SIDI engine decides the importance of the received streams, and depending on the information they provide it decides two things. So simple cases, coolant temperature monitoring, it generates an alert right on the app, and for complex cases it sees that there are many more events happening, then it transmits the filtered streams to the backend servers and let the backend figure out, because it does not appear to be based on just one single isolated sensor measurement which is just coolant temperature rise, remaining parameters are all fine, then you have no way of concluding what the problem is, so it has to give it to the backend. So the other portion of the CEP running on the backend has the freedom to work with large database, performing complex processing. Maybe a simple analysis that is happening on the phone is insufficient, it will have to look at some unusual patterns and then generate alerts. So all of that is captured in the backend part. So this is one thing. Then the whole framework also has the ability to do this very critical thing, performing long term analysis. Okay, it should be able to predict undesirable outcomes such as failures of sensors well in advance, and so this paper goes into those details. It does something about driver monitoring, which is an important thing, and it captures this by using lateral acceleration and longitudinal acceleration. So, this is how it captures reckless driving. Okay. So, any sudden variation of the longitudinal acceleration is a good measurement to detect reckless driving, and it was decided to use in this case. How to set it up, processing within the app, this is mentioned here. Okay. How do you get acceleration, lateral acceleration and longitudinal acceleration, that is the question, right. This you can get from the speed itself. You see, Siddhi engine transforms speed streams into acceleration deceleration streams by considering consecutive speed readings using the following Siddhi query. So, you actually generate reckless driving behavior from the speed measurement itself. What should be the acceleration deceleration and what should be the threshold, where should you set it? Well, the threshold should be set at 4.5 meters per second square, and this is a standard. You cannot accelerate greater than this. Okay. So, if you do that, that means you have actually violated the safety norm. So, this is what is a clear indicator that the driver is really reckless and he is going much higher than this. So, what you do is you get it over a period of time and you count the number of 1 and 0 assigned to the points which have an acceleration deceleration and apply the threshold and have an acceleration higher than the normal threshold and to normal points respectively, and total number of ones are counted over a predefined time period, and by this count you classify according to the driving cycle, okay, whether it is a traffic, normal, highway and all that. Okay. The driving cycle is determined by the average speed of the vehicle throughout 10 minutes. The count together with the class is sent to the backend server periodically as separate streams for acceleration and deceleration. So, you can see lot of information is being already generated from just the speed related information, and so very useful data is actually got directly from the speed itself. Okay. This is the nice takeaway from this part of the discussion. Now, what does the backend do? You have to do some processing on the backend. So, backend does get the data and it is summarized. You have the business activity monitor which can be set to hourly, weekly, monthly and all that, and there is an SQL database ready to be read by the web portal. It does that, it just takes the data and puts it there. Alright. Next is detection of driving anomalies. This is again referred to by another paper and they gave reference of that paper, and the point is that if you want to detect driving anomaly, it is a research area and you can investigate this all by yourselves by looking at several papers in that. The paper here is actually talking about creating a Markov model which was used to determine the difference between the current pattern and the existing pattern of a driver. So, that is essentially you find the difference, right, the current pattern and the existing pattern of a driver vehicle combination. So, you start identifying driving anomalies and put them into 3 different stages. There is a pre-processing stage. So, speed to acceleration streams, from acceleration streams you put it as acceleration transition streams. So, that essentially means you get the timestamp, previous acceleration and the current acceleration. These streams are then communicated to the backend twice actually, once to the CEP in real time for calculating whether the readings are in accordance with the normal pattern, and next to the BAM daily for updating the model. So, you can see that one is to the CEP, and so you can see here that you may have to send it twice for this model, for this block and to that block as well. So, you from there you find out the driving anomaly, you do twice transmission, once to the CEP in real time for calculating whether the readings are in accordance with the normal pattern, because it is the CEP that captures the any anomalies, right, and BAM for updating the model, right. Creating the model, what is the model here? The model indeed is a Markov model, and that model is stored in some sequential database. The BAM essentially processes the events, acceleration transition streams received from the app and updates its transition table consisting of transition probabilities daily. Therefore, more accelerations of the BAM receives. As and when it gets more and more data, the model becomes much more accurate. You do the anomaly detection using by calculating the probability of Markov chain resulted by the recent accelerations. Appears to be quite straightforward, and then CEP, after it receives an event, that is the acceleration transition stream, it calculates the average transition probability for 5 minutes using a sliding window on the timestamp with the aid of transition probability table stored in the database by BAM. The average probability of each chain of accelerations is calculated using the property highlighted in this expression here, and once it drops down to a predefined threshold, an alert is sent. So, you can see this is the acceleration transition diagram. Similarly, vehicle diagnostic, if you run through, you will see that you can look at oxygen sensor, which is important aspect, which is more like an output from the whole engine manifold system, because you know what is the amount of oxygen that is coming out. If it is a large quantity, then you know that it is unburnt, it is just coming out, that there is efficiency problem, and there is, you need to do something about the air to fuel ratio mixing, right. So, you can do some sort of regression analysis of this oxygen sensor failure, and you can see that this picture is actually capturing that. It is telling you what should be the threshold and where exactly the problem comes by simple thresholding. Similarly, you could do with mass airflow sensor. As I mentioned to you, the MAF sensor is placed between the air filter and the throttle body, and it is typically measured in grams per second, and you can see that there is also the MAF flow rate versus RPM. In higher RPMs for a normal sensor, right, there is a normal value and then there is an anomaly. Then you should also be able to say what is the faulty sensor, right, flow rate versus RPM. For a faulty sensor, you would get typically like this. The pictures are pretty different, as you can see, and regression analysis is done periodically and corresponding gradients are stored in the database. So, you can do some very simple things to get to understanding whether there is a problem with respect to the MAF sensor, whether there is a faulty MAF sensor, right. And I mentioned to you, all big companies have to do something very simple like this if they have to really predict if there is a problem with the MAF sensor. Then you go on to read this, you will find that engine coolant is also something you can put a threshold, and then if it crosses that threshold, you mention that the engine coolant temperature has increased. So, one can go on with the oil temperature monitoring. You get a mode 01 PID, which is 5C, right. So, you can clearly see that this is from the traction or the part where when we talk about the powertrain, this PID is also from the powertrain, and therefore, if oil temperature is low during RPM is high, the produce water and sulfur as byproducts of the combustion process can form acids and damage engine bearings. So, I suggest and strongly recommend that you read this paper and also download this tool here. You can see the name of the tool here, it is called Campana. You can also download this tool and sort of play with the tool, get familiar with the tool, so that you exactly know what is happening with the engine ECU related parameters. So, driving anomalies are shown here, and you can see that speed patterns are given as inputs, alright. So, you know here that this is one is anomalous driving and normal driving. You can see how the results look, and that will give you an idea of what is capable from an IoT person to improve safety, to improve reliability of these vehicles. Alright, so that is about this paper. Let us move on to see a demonstration of this complete system to understand this better.